Today's lesson is about current voltage graph, and the objective of this lesson is to sketch and explain the IV characteristics of some electrical components. Metallic conductor or wire and resistor, they have the same IV behavior. In both, current is proportional to voltage, which means no voltage, no current. Also, both wire and resistors are not polarized. But since the voltage is polarized, then the current will flow according to the sign. If it is a positive sign of the voltage, the current is flowing in one direction. If it is negative, so you revert the polarity of voltage source, the current is going to flow in the opposite direction. This simple circuit explains better. So here we have the terminals of a resistor connected to the positive and the negative terminal of the battery. So the current is going to flow in this direction. However, if the battery terminal is reverted, the resistor, even though it's not polarized, but the current is going to flow in the other direction. Because the conventional current, this is the battery, this is the negative, this is positive, the current always flow from the negative to the positive terminal of a battery. So that's what happened here. So it was reverted and the direction of the current changed. If you are asked to design a simple circuit that you can read current and voltage across a resistor, so this is a good example for you. So here is the voltage supply, the N meter connected in series to read the current. This is the resistor, and here is a variable resistor. So we can change the variable resistor to create a different current flowing, therefore a different voltage drop on R. So from this, we can collect enough information, make like a table, and read the current on this N meter and the voltage on this voltmeter. It starts with 0, which means no voltage, no current. And from here, through a data table, draw a graph. So this graph would look like this for a resistor. The IV characteristics for a resistor is that the graph is a straight line passing through origin, which means no voltage, no current. And on the other side here means that negative voltage, the current is going to flow on opposite direction. So this is this graph is showing a straight line, which means the component, in this case a resistor, obeys Ohm's law. What that means? Ohm's law states that current and voltage are directly proportional. So there is a proportionality here on this line, which is stated by Ohm's law. So it's important to note the temperature must be constant to have a straight line like this. Now, this spring inside this light bulb is the filament lamp. So I'm going to try to bring closer. So as you see, is a spring that is connected on both ends. And what happened here is that the current will flow through these many turns, and over time this spring is going to become hotter and is going to emit light. So design an experiment at which we can draw a graph from what's going on with this light bulb. So we need a voltmeter and you need the N meter in the circuit, and we can notice that through the origin and up to certain point. So this line is going to behave just like a metallic conductor or resistor. But because over time, because so many turns, the temperature is going to rise and is going to change the value of the resistor. So which means that no longer will obey Ohm's law. So now up to here obeys Ohm's law on both sides, but then will not, the current and voltage, they are not going to change at the same proportion. So then we have this curve like this on this quadrant and this quadrant. But sometimes on your exam, they just ask this quadrant right here. With this brief explanation, let me do a practice problem that involve the filament lamp IV graph. So A, describe IV characteristics of a metallic conductor at constant temperature. So this is how the graph should look like. You can do just one quadrant. You don't have to do like all the way down. Just one is fine. As long as it can be described as a straight line through the origin. Before going back to the problem, let me explain something about diode. This is a diode. This is a close look of a diode. If you notice in this side, we have this line, this mark. This is the negative side of this diode, and this is the positive side. A diode is a polarized component, which means that the negative side must be connected to the negative side of the circuit, and the positive must be connected to the positive side of the circuit. Also, a diode requires a minimum voltage and current requirements. Here is the graph of a diode. So, on this negative side of voltage, current will not flow. Now, what happened on the positive side? Is it still will not let current pass through until the voltage has a minimum value required by the manufacturer. So, and then after this, the current will flow in an exponential way. Back to the problem. So now it's asking to describe the IV characteristic of a semiconductor diode. Now this word semiconductor means that the diode is a conductor with certain conditions. One is that we have a minimum voltage and polarize, and then becomes a conductor. So there is no current for one direction. So in this direction here, negative direction, there is no current up to few voltage, then increasing gradient. So that is the description of, for your test, refer to a semiconductor diode. Now the next question is about filament lamps. Two identical filament lamps are connected in series and then in parallel to a battery of electromotive force 12 volts and negligible internal resistance, as shown in picture A and B. A very easy conclusion of this diagram, this circuit. Both lamps are the same, and both are connected to a 12 volts battery. So we can say that the voltage drop on each light is the same, which is 12 volts, will be 6 volts here and 6 volts here. So now what we are going to do is you're going to find the 6 volts and connect to the current using the graph provided on the next page. So for the 6 volts, the current flowing in this lamp is 2.8 amps. What about the voltage on on this lamp? Well, both lamps are in parallel and connect directly to the battery. So we can say the voltage on each lamp is 12 volts. Okay, so using the same reference graph for the filament lamp, so 12 volts, this blue shade here, corresponds to a current of 4 amps. So here is asking, with the information from this graph, determine the current through the battery, not through the lamp, through the battery. For circuit 6-1A, so no calculation needed here, just follow the graph and you got 2.8 amps. Because all three components, the battery and the two lamps, they're in series, so the current flowing through the entire circuit is the same. So right here, the current flowing through the battery and the entire circuit is 2.8 amps. The next question is, so what is the current flowing through the battery when the lamps are in parallel? Okay, remember, this graph is about the lamp, not the battery. So the current flowing through the lamp is 4. So the current flowing through the lamp for the parallel circuit is 4. But it's asking what is the current flowing through the battery. So here we have a junction, and those two currents, they are going to combine or recombine. And now I have a current flowing through here of 8 amps. So the current flowing through this battery should be 8 amps. So to answer question 2, no calculation needed. So the current flowing through the battery is the current flowing through the lamp 1, which is 4, and the lamp 2, which is 4. So the current on the battery is 8. Next question, calculate the total resistance when the circuit is in series. So here we have two light bulbs, the same, and they are connected to 12 volts. So the voltage on each one is 6 volts. So let's calculate the resistance just one lamp. So that is 6 divided by the current flowing through the lamp, which is 2.8. We obtain this value graphically. So dividing 6 by 2.8, we have 2.14 ohms, but it's asking the total resistance. So in the total resistance, in this case, we need to add both. So the final answer is 4.3 ohms. Okay, what about in parallel? So in parallel, we can calculate the value of the resistance the same way. Now the voltage in parallel is 12 volts. And the current flowing through the lamp is 4. So 12 divided by 4 is 3. So because they are in parallel, so we do the inverse of 3 plus the inverse of 3. And the result, we inverse one more time, and the answer is 1.5 ohms. Last question from the same problem. Calculate the ratio of the power dissipated in the lamp when in series and the power dissipated when it's in parallel. So we can use the formula I square R for each series and parallel. So the I here is 2.8 and the square times the resistance that we calculated and divided by 4 square times 3, and this is the result. So the ratio is 0.35. Next question is about the IV characteristics for a diode. So that's from May-June 2015, paper 21, question 5. The variation with potential difference PD of current I for a semiconductor diode is shown in this graph. So the question is asking to use this graph to describe the variation of the resistance of the diode between 0.5 volts and 0.8 volts. So negative 0.5 volts is right here, and 0.8 volts is right here. I want to bring this graph a little bit closer to identify 0.8 volts, which is right here, and 0.8 is and be right here, right? So yeah, like touch the graph all the way up. So let me look with you the bottom one here, from negative 0.5 volts up to, so each 2 marks is 0.1, so 0.1, 0.2, 0.3, 0.4. Looks like from 0.45, so a little bit of current starts to flow here. Meanwhile, from negative 0.5 to positive 0.45, there is no current flowing. We can say that the resistance in this diode is so high for this range that current cannot flow through it. So how to answer this question? You can say high or infinite resistance from negative 0.5 volts to positive 0.45 volts. The next one, you can say the resistance decreases after positive 0.45 volts. You can see that by the increase of the current. Then the next question is asking to sketch the variation with PD or voltage of current I for a filament lamp. Numerical values are not required. So how you can get your points from this? First, initial straight line through 0, like this. Straight line through 0, because it's kind of obeying Ohm's law at this point. So you know that the filament has all those terms. So it's still the current and the voltage, they are directly proportional. So as the filament gets warmer or hotter, so and then there is no proportional anymore. So one thing you can say here is the initial straight line through 0 into curve decreasing gradient but not horizontal, and repeat in negative quadrant. Okay, now we have another story going on here. It still relates to that filament lamp. Now we have a circuit. So this circuit shows a power supply of a EMF of 12 volts and internal resistance 0.5 ohms. So the internal resistance is part of the cell, connected to a filament lamp and a switch. The filament lamp has a power of 36 watts and PD across of 12 volts. I calculate the resistance of the lamp when the PD across is 12 volts. Now you may think, how is this possible? The switch is open, there is no current flowing here. How come do I have 12 volts of PD here? And what about this resistor? This voltage is not kind of splitting between both. All your thoughts are correct. One thing that we need to add here is the manufacturer specification of the light bulb. So the light bulb came from the manufacturer, printed 36 watts, and the voltage across of 12 volts. And in that case, what is the resistance of this lamp? For example, this is a big light bulb, right? So if you turn over here, all light bulbs, they have a specification printing on the device, or you can also have on the box, right? The box that come with. And here you can see 150 watts and 120 volts. So we can calculate the value of the resistance of this light bulb using this information. We don't have to connect these to actually calculate the resistance. We can use the specification here on this light bulb and calculate, but we are gonna do with the problem that is from the question. Okay, so when the lamp is not operating, so we have P is equal VI, so which means that I is V over R. Now we have V squared over R, and now we can do our substitution. The power is 36, V is 12, and we can calculate R, which is 4 ohms. Okay, so the next question is asking, now the lamp is working. It's connected to the circuit, the switch is closed, and the current flowing through the lamp is 2.8 amps. Calculate the resistance of the lamp. Okay, just to compare here a little bit, the first question is asking to find the resistance when the lamp is not operating. And the second question is asking to find the resistance when the lamp is operating and there is a current flowing through it. So I'm going to use the Kirchhoff's second law to find this resistance, this new resistance. So the sum of EMF, in this case is 12, is equal to the sum of the PDs of the circuit. Now, it's providing a current of 2.8 amps, right? I'm going to use this here. So my PDs is 0.5 times 2.8 plus the value of my resistor of this lamp times 2.8. Okay, a little bit more formal. So the EMF is equal to the sum of PDs, right? The PDs on the lamp and PD on the internal resistance. So PD on the lamp is the current times the resistance of the lamp when it's operating plus the current times the internal resistance. So the current was given, which is 2.8, and the internal resistance was given, which is 0.5. So I calculate the resistance of the lamp when it's working is 3.8. Okay, so it's a little bit less than if would not be working. D, explain how the two values of resistance calculated in C provide evidence for the shape of the sketch you have drawn in B. Before I answer this question, let me organize my thoughts using this table here. So there's two scenarios. One is the resistance of the lamp when it's not working. So when it's not working, we calculate as 4 ohms based on that was provided a voltage of 12 volts. So what will be the current in this case? So the current is V over R, which is 12 divided by 4. So the current here is 3 amps. Okay, what about when it's working? What do I have? So when the light bulb is working, so I calculate the resistance, which is 3.8. The current was given in the problem, which is 2.8. So what is the voltage now? So that will be 3.8 times 2.8. And I have 10.64 volts. Okay, so I can use these values here to justify how I obtain that straight line, because current and voltage are directly proportional. Look at this. I have, let's say, for a voltage of 12, my current is 3. The voltage dropped and the current also dropped. So there is a proportionality here which can justify that graph. So to answer the last question, explain how the two values of resistance provide the shape that we sketched on the prior question. So we can say that when V or R increases, R also increases, or resistance increases when current over voltage increases. Next, I want to talk about the graph of a thermistor and a LDR, not based on IV characteristics, current and voltage, but what actually trigger the change in resistance. So for example, a thermistor is a resistor which resistance change with the temperature. So here you can see that when the temperature is going high, so the resistance is low. And when the temperature is low, the resistance is high. So that's pretty much the type of graph for a thermistor. Likewise, for a light-dependent resistor, which is a type of resistor which its resistance changes with the amount of light. So here is a graph with the light over the resistance and the same behavior. So as the light is brighter, so the resistance is lower. As the light is less bright, so the resistance is higher. Also part of today's notes, the symbols for different components is showing here. The resistor is just like a box, right, with those two terminals, not polarized. The light bulb is a circle with an X. The diode is polarized, so make sure that you indicate the negative and positive terminal. Thermistor is like a resistor with this line and a little small like parallel line here. And the variable resistor, there is a arrow indicating that it's changing. And the LDR is also like a resistor with those two arrows indicates the light hitting these components. Okay, from the past exam from May, June 2015, paper 22, question 5, on this picture, sketch the temperature characteristics of a thermistor. You need to make sure that you hit some points here. One is this line must be curved, decrease in gradient, a smooth line, not horizontal, and no touching X or Y axis. Then the next problem, we have an application of a thermistor connect to a circuit in series. So we have here a resistor X, Y, and Z. X and Y, they are fixed resistors. Z is a thermistor, and that's the voltage supply, 12 volts. Okay, so that's the written explanation about the circuit. A battery of EMF 12 volts and negligible internal resistance is connected in series with resistors X and Y and thermistor Z. The resistance of Y is 15 kilo ohms and the resistance of Z at a particular temperature is 3 kilo ohms. The potential difference PD across Y is 8 volts. Okay, back to the picture, to the circuit, but with the data provided on the resistor Y, the PD across this resistor is 8 volts. The value of this resistor is 15 kilo ohms, and the value of this thermistor at certain temperature is 3 kilo ohms. Question I. Explain why the power transformed in the battery equals the total power transformed in X, Y, and Z. Here is the answer. Because the internal resistance of the cell or EMF, R, is negligible. So all the energy from the battery is transformed in X, Y, and Z. So those three resistors, they're going to use all that energy from the battery just for those three components. Calculate the current in the circuit. Super easy here. So all those three components, they are in series with the battery, which means the current flow in the circuit is the same. And is giving information about Y, which is 8 volts and 15 kilo ohms. Okay, so I can use this information to calculate the current flowing through Y, which is the same current flowing through this entire circuit. So 8 volts over 15 kilo ohms is You do your calculator, calculate a job here, 0.53 milliamps, because these 10 to, you can keep like this for now, 10 to the minus 3, or you can use the prefix milli. Okay, so if you want to use the space provided and do your calculation, you should. So I is equal V over R. This is just for the resistor Y resistor. So it's 8 over 15 times 10 to the third, because this is kilo, okay? And doing your calculator is 0.53 milliamps, or you can do just 10 to the minus 3 amp. Now, calculate the resistance of X. So back to the circuit. So why not use the Kirchhoff's second law? So we have here the EMF, and you have PD on X, Y, and Z. And you can use this Z as 3 kilo ohms, because did not specify that in certain temperature, just was that the information was given. So we can use the Kirchhoff's second law and calculate the value of X. So here is 12 is equal the current times X plus, I already have the PD on Y, which is 8, right? Plus the current flowing through the thermistor and the value of the thermistor. So the value of X is 4.5 kilo ohms, or 4.5 times 10 to the third ohm. Okay, question about the thermistor. The temperature of Z is increased. State and explain the effect of the potential difference across Z. Okay, so 2 points here. One is that with the increase of the temperature, so the thermistor resistance is going to decrease. That way, the current flowing through the circuit is going to increase. So you can say this way. Resistance decreases, then current in circuit is greater. The second point is that, now what happened to the voltage? So the PD across X and Y now is greater than the PD across Z, because Z as Z decreases.